Hello, I'm James Charles and I will present our work on Style2NeRF, which is an unsupervised one-shot NeRF for semantic 3D reconstruction. First, consider this image. Although the image is two-dimensional, we as humans can recognize the objects that are within it. We can imagine what these objects may look like from different viewpoints. And we understand the orientation of rigid objects and which direction they're facing, and also the 3D pose layout of the parts of articulated objects, such as people and their pose. Furthermore, we can hallucinate what these objects may look like with various semantic attributes changed, such as adding a second story to this building, or what this car may look like coloured orange, or what two different people may look like wearing the same outfits. And the first goal of this work is to build a computational model which can do the same thing. And we demonstrate this model on the class of cars. So provided with a pre-segmented car image, the model should be able to infer the 3D pose, generate new viewpoints, and have some sort of semantic control. The second goal is to train this model from completely unlabeled image collections, such as single-view images of car instances, without any 2D or 3D annotation. Our model is novel compared to prior works such as Pix2NeRF or StyleGAN Render, in that we can directly regress to a semantically controllable NeRF from a single image input. Our model also produces pose estimates, and we show how to improve these estimates by mitigating a pose and viewpoint ambiguity problem. And the model also has a nice property which allows us to transfer from synthetic data to real image collections. Style2NeRF works by taking an input image and encoding it to a StyleGAN code. A transcoder then maps the StyleGAN code to a shape and colour vector, which directly controls a generative neural radiance field, or NeRF for short, through a NeRF decoder. Let's take a closer look at the NeRF decoder. The NeRF decoder is a function f which takes a spatial location as input and produces an RGB and volume density at the output. It consists of two networks, a colour siren and a shape siren. These are fully connected networks with a film activation function. These are sine functions which can be modulated by a frequency gamma and phase shift beta. Mapping networks take the colour and shape code and map them to appropriate frequencies and phase shifts, modulating the whole network so as to render an output image which is as close as possible to the input. And of course, as this is a NeRF model, we can also render alpha masks, depth masks, and novel viewpoints. Next, let's take a look at the transcoder. The transcoder is split into two parts. There's a style mapping network, which regresses to shape and colour codes, and a camera regressor, which regresses to the azimuth and elevation of the camera. To train the model, we first pre-train the encoder using an off-the-shelf StyleGAN inverter. We use Restyle, and then this becomes fixed throughout the rest of training. Training is then accomplished in two phases. In the first phase, we pre-train the NeRF decoder like a GAN. And in this way, we sample color and shape codes, as well as camera poses, usually from a known distribution. And then we have an adversarial loss, which ensures that the renders look like they come from the training data. In phase 2 of training, which we call fine-tuning, we now sample StyleGAN codes, and for each StyleGAN code we generate the corresponding StyleGAN image, which becomes our target, and this allows for fully supervised reconstruction losses to be used for training. As we backpropagate, the transcoder learns to map the 2D StyleGAN code to these 3D shape and color codes which control the NeRF decoder. The transcoder predicts camera pose, and we propose inverting the camera pose to produce object pose. However, this causes an issue in that all objects generated inside the NeRF volume need to be canonicalized and point in the same direction. We enforce this by introducing a symmetric inductive bias, which assumes the object has a single plane of symmetry, which many man-made objects do. And during the rendering process, rays are reflected off this plane, querying only half the NeRF volume and mirroring the other half. This is a very strong constraint and locks one of the three rotational axes. For the other axes, we use a principal direction loss. And this enforces the principal axis of the NeRF volume density to lie against one of the coordinate axes. Without pose constraints, renderings of from fixed viewpoints can contain cars in various orientations. However, with the pose constraints added, everything becomes nicely aligned. We test our method on the SRN Cars dataset, which contains thousands of images of synthetic cars with a known pose prior, and observe that qualitatively, when presented with an input image, our model can reconstruct the input very well and give accurate 3D pose estimates, and also generate plausible novel views. Compared to the state-of-the-art model, Pixel NeRF, our model produces better structure and less blurry results, particularly for the unseen side of the car. We also test our method on a dataset of real car images. Here we do not know the pose prior, and this can cause problems with training because we don't know the correct camera pose distribution to sample from in phase 1 of training. And this causes degenerate solutions such as billboard effects and floaters. However, our model has a nice property which allows it to be pre-trained on synthetic data, such as SRN cars, and transferred to real data, which solves this viewpoint distribution problem. So we can pre-train our model on the SRN cars and fine-tune the model in phase 2 on real cars. The reason why this works is because we have a StyleGAN representation in our model, and this has a nice property in that that StyleGAN, when trained on the synthetic data under optimization, can fit to real car images. So during training, our model also utilizes this property, allowing us to transfer from synthetic data to real data. Qualitatively, we can reproduce the shape and color of real cars reasonably well. There are some artifacts, such as at the rear of the car, and this is probably due to there not being as many rear car viewpoints in our dataset. Style2NeRF is semantically editable in 2 places. We can manipulate the StyleGAN code, or we can manipulate the NeRF code. Here we show StyleGAN manipulation, whereby we transfer the style of the top row cars to those in the column, making this white car here have a sunroof, or be yellow or red, and similarly for the other cars. Here we show the NeRF code manipulation, taking these 3 example cars and sampling different color codes while maintaining the same shape. Quantitatively, we evaluate pose estimation performance against a fully supervised baseline. This is a ResNet 34 network, and we measure the error in elevation and azimuth. For the SRN Cars dataset, the azimuth error is rather large, and this is because of the front and back-facing confusion. To show that this is the case, we also measure the min azimuth error, which is produced by computing the error of the predicted pose and also the error of a 180-degree rotation of the predicted pose around the vertical axis, and then recording the minimum. This large drop in error indicates front and back-facing confusion is the main cause. Comparing our model without pose constraints shows we perform well under elevation, but poorly under azimuth. However, once pose constraints are included, our unsupervised model now actually performs better than the fully supervised baseline. For the real cars dataset, although errors are higher in general, the story is similar, with our unsupervised model being on par with the fully supervised baseline. We then measure reconstruction quality using the CARLA Cars dataset and compare our method under the usual metrics, showing we outperform the current state of the art. In summary, our model, Style2NeRF, is an unsupervised one-shot NeRF which can produce pose estimates that even outperform a fully supervised pose estimator, albeit a simple one. The model is semantically editable and can be trained via transfer learning on real data where pose distributions may be unknown.